So at the end of the last lecture, we were in the middle of this example here where we're using scanf. So the scanf function reads a string and tries to extract information from that string. And so the way you use scanf, here's an example right here. You pass in the string that you want to parse or read. You tell scanf, how would you like to extract the information from that string? And then you tell scanf, where would you like to store that information? The thing you have to remember about the last part is the where would you like to store that information is that scanf needs to write into a variable owned by the caller. So that variable there has to be a pointer of some kind. Right. So in the first example, Larry, can you close the door at the back? Thanks. Thank you. Okay, so in the first example here, we want to scan the empty string. I want to scan the contents of that string as though it were a string. I would like to store that string into str1. Right, str1 here is an array up back here. Right. Oh, wait a minute, I have the mouse. So str1 is an array, but remember the name of the array is synonymous with a pointer to the first element of the array. So that actually is, as far as C is concerned, is a pointer. Right. The return value from scanf is the number of successful conversions. Right. So here there's one attempted conversion. Right. If you run this example here we get n equals -1. So why do we get -1? So the return value is the number of successful conversions, or it's equal to this value called EOF. Back here somewhere, way back here somewhere. Where to go? Format. Here it is. Right. So it's equal to EOF, which is usually negative on most systems. The actual value is not specified. Right. If you reach the end of the string that you're scanning before any conversion is attempted. So back here, right, when scanf looks at the empty string, it reaches the end of the string before it actually sees a string. So it returns the value EOF, which on my computer is -1. Right. Now remember, most of these conversions will consume all empty space or a blank space before attempting to do the conversion. So if you try to scan a string that contains only spaces, and you'd like to interpret that as a string, which is not an unusual thing to do, right? You might want to read a bunch of empty space. That doesn't work with the %s conversion, right? So %s consumes all of the blank space, all of the white space, before it attempts the conversion. So if you consume all the white space here, there's an empty string, and again, it fails to convert. Right? So again, you get -1. The second example, the third example, sorry, we're going to scan the string ABC, and we'd like to extract an integer from that string. Right now, there is no integer here, right? So scanf looks at the string, it looks at the A, it says I can't convert that to an integer, it stops, right? And it leaves the A on the input, right? And then in this case, so the %d means convert as an integer, so it fails. Right, and now you get back to 0 in this case. Right, so the third example is it performs no conversions. Right. Again, notice the use of a pointer here. Right, scanf needs to write into a variable owned by the caller. I would like them to write into the variable y1. Right? The only way that the function can write into the variable owned by me is if I pass it a pointer to that variable. So we have to pass it the address of y1 here. Okay, it's not till the fourth example where something actually works. We're going to scan the string ABC. I would like to extract a string from the string ABC, store the string in str1. So that actually works. Scanf tells us it was able to successfully convert one thing, right? The string, and the resulting string is ABC. Right? Scanf always writes the null terminator into your string for you with the %s conversion. Right. So if you're using that conversion there and it succeeds, the null terminator is written into the string for you, guaranteed. The conversions, most of them will stop when they encounter a space. So here it's %s. I think the original example of this, I think this is modified. I think the original looks like this. And then this one has to change. So that's the original notebook version of this. If you run that, you get the same thing as in the previous example. Okay, so here, we want to scan the string ABC space XYZ. We'd like to scan it as though it were a string, or I'd like to extract one string from that string there. So I'm going to use %s. Right now, the %s stops reading when it encounters white space. So it sees the string ABC, then it sees the space, so it doesn't consume the space, and it only writes the string ABC into str1. Right. If you want the XYZ, then you have to read that into a second string. Right, and so that's why the previous version that was there had the following. Right. So this says read a string and then read a string. Remember, %s will consume all leading white space. So it reads the string ABC, right? Encounters a space, so it writes ABC into str1, right? And now there's a space XYZ. So it consumes the space now and then reads the string XYZ and writes that into str2. And so if we put this back to the way I had it before, right? Now you'll see that it also reads the string XYZ right there. All right, next example is, where's the next example? Here. Here we've got ABC space 1 XYZ. Right? So if you wanted to consume all of the information in that string, one way to do it would be to read in a string, followed by an integer of some kind, followed by a string. Right? And so you can use the conversion %s, %u, %s, right? String, unsigned integer string. Right? I'm going to write the first string in str1. We're going to write the second, the int into x1, and then the second string into str2. Right? And that works just fine. Right? You get 3 conversions, and the strings ABC, XYZ, and the value 1. Now, if you have a string that contains a bunch of stuff in it, so in this case, it starts with an integer, it starts with a number, and then has some extra characters in it. Right? If you try to convert that, in this case, using %d, that does in fact work. Right? So you can in fact extract the 99 or the -99 out of the string. Right? So what scanf will do is it'll see the -99, and then it sees the A, right? So it concludes, okay, so there is an int here, right? The int -99 is in fact here, so we'll write that into y1, right? And it leaves the ABC alone. Right? You get 1 conversion, and the value that's the int value that's read in is in fact -99. Okay, almost done. Here we've got a string -99, comma, -1.5. There's a bunch of extra spaces all over the place. Right? We can scan that string in as follows. Right? So here we can extract the int part as using %d. Now, we've got a space followed by a comma. So if you want to consume that to get to the double part, right, you can put in a space. If there's a space in your formatting string, then that space matches 1 or more spaces. Right? And so it'll match this. Right? If you insert extra spaces in, it'll also match that. So that's fine as well. Right? It'll then match the comma. Right? Here, the space isn't in fact necessary, but if you put it in, it'll consume all the spaces here. Right? And then it'll try to read a double. Right? And so with scanf, if you want to read in a double value, it's %lf, not %f. Right? %f will read in a float. And that works just fine. Where's the last one? Okay, so this is the example here. Right. And finally, the last example here, we're going to scan a non-blank string for a single character, right? So %C on its own, right, reads in one character, right? And it'll also read in a space, right? So here it's going to read in the minus sign from the string, and you get the minus sign here, right? If you put in a space here, right, %C is one of the two conversions that will not consume white space automatically, right? So if you tell it to read a character and that character happens to be a space, it'll actually read in the space, right? So if you're trying to read in something that has spaces in it and you want to preserve the spaces, you probably can't use %S, right? You probably have to use %C instead. This is an extra notebook that shouldn't be here. Sorry, an extra cell that shouldn't be here. There we go. Okay. What time is it? All right, so I guess we'll do this part and then we're going to skip ahead to the next notebook. The %square bracket conversion lets you specify which characters should be matched or which characters should not be matched. Right, so %square bracket and then some set of characters inside the square brackets, right, will match a non-empty string made up of any one of the characters in this set. Right, so if you had %square bracket ABC, it will match any string made up of the letters A, B, or C, right? Sorry, and C, A, B, and or C, right? So A, B, B, A, B, A, C, C, A, A, anything like that, it'll work, right? So for example, well, here it is. %ABC will match any string made up of the characters A, B, or C. Right? If you want to specify which characters not to match, you can put in the little caret in front. Right, so caret followed by a set of characters will match any non-empty string that does not contain one of the characters in that string. Right, so not ABC will match any string not made of the characters A, B, or C. Right, so X, Y, Z is fine, X is fine, 1 is fine, right? But if as soon as it sees an A or a B or a C, it will stop matching. Right? This is the second kind of conversion that will not discard white space before attempting a match, right? So again, another way to try to read in something that contains white space is to use % and then square bracket. There's no often when you're doing this thing, you want to read in a range of you want to specify a range of characters. So you'd like to say, I'd like to read in all the lowercase letters. Unfortunately, there's no portable way to do this. Right? And so the C standard says there's no guaranteed way to write a range of characters, right? Even though everything else you've done, right, in Bash, for example, you're often able to write something like that, right? So unfortunately, you can't specify a range and have it work on every compiler, right? If you're working with GCC, GCC almost certainly lets you specify a range of some kind, but there's no guarantee it's going to work everywhere. And so this thing is handy if you're trying to extract data from a character delimited string, right? So a character delimited string is something that looks like this. Right? And it's very common when you're reading in data files that each line of the file contains a fixed number of pieces of information, right? So here we've got last name, first name, student number, or something that looks like that. Right, so you can imagine a file containing all the students in a course, right? And they would all have, each line of the file would look something like that, right? It would also not be surprising to see spaces somewhere in these characters, in these strings, right? So for example, someone might have a last name that's made up, a quote unquote last name that's made up of several different names, several, like all their middle names as well, right? That's how OnQueue stores things, for example. Right, it either puts all of your names in the first name or it puts them all in the last name. Right. Okay, so if you wanted to read in something like this and you're worried about spaces, right, you can do something like that. Right. So you look at that thing, you say, well, what the heck is this? It's saying there's a caret and a comma, right, inside square brackets. So that says read in any non-empty string, right, that doesn't contain a comma. So if you start at the front, right, it keeps on going until it sees a comma, right, and then backs up, right? And so the first conversion there will result in the string Simpson. right? Now you need to consume the comma, right? So the comma has to be here in your formatting string, right? So it'll now eat the comma and then read anything that's not a comma, right? So now it's going to consume Bart and store that in the first name, right? Consume the comma, right? So make sure the comma is here in your formatting string, right? And then consume the last part of the line, which is an unsigned integer, right? Store that in the student number, right? Don't forget to pass in the address of the student number because you need a pointer here. And so this thing does what you'd expect it to, right? Tells you the name is Bart Simpson and the student number is 1, 2, 3, 4, 5, 6, right? If there are spaces in one of the fields, right, that works just fine, right? Bart, what happened here? Oh yeah, sorry, it's too long. Haha, overflowed the buffer here. So there we go. There you go. So now it works correctly. All right, so the last thing I'm going to talk about is %n, because this is often handy when you're trying to read a file. So when you're reading a file, it's often useful, or sorry, reading a file or a string, right? It's often useful to know how many characters have actually been read so far, right? And there's lots of reasons why you might want to do this, right? So if you need to find out how many characters have been read by scanf so far, you can use %n to get that information out, right? And so this turns out to be quite handy to have around. So you can use it as many times as you want, right? So here I've got %n twice, right? Each time you ask for the number of characters that have been read so far, you need a variable to store that in, right? So I've got I1 and I've got I2 over here, right? So the first conversion reads in the last name, right? The second conversion tells me how many characters have been read in after the last name has been read in, right? The third conversion reads in the first name. The fourth conversion reads in how many characters have been read since reading in the first name, right? So it's the %n, if you do it twice, right? That second one is the number of characters that have been read since the previous %n, right? And then so on and so on and so forth. So here, if you run this little example, right? It reads in Simpson, right? Now, the number of characters that have been read so far, you can treat that as an index for the first. So that is the index for the comma in this case, right? So if you read in the characters of the last name, sorry, if you read in the characters of the last name, that's 1, 2, 3, 4, 5, 6, 7, right? If you treat that as an index, then that's the index of the comma, right? Sorry, what happened here? %n. Sorry, the second %n is the number of characters that have been read up to this point. Sorry, it's not the number of characters that were read previous to the previous use of %n. It is the total number of characters read. So I2 is going to be the index of that comma there, right? That's this %n right there, right? So read in the first name, or sorry, read in the last name, right? Tell me how many characters were read. Read in the comma, right? Read in the first name, right? And now tell me how many characters have been read in the entire string, right? So read in the last name, right? Tell me how many characters have been read. So that's the index of the comma, right? Now read in the comma and read in the first name, right? If you treat that as an index, that's the index of the second comma, right? And then read in the rest of the last name, right? And so I'm going to use the I1 and I2 to simply replace the commas in the original string, right? And so you get that there, right? Okay, so the rest of this notebook I'm going to leave as optional. So if you want to read the rest of the notebook, and there is a fair bit more actually in this notebook. So there's a lot you can do with scanf and sprintf. So for the time being, I'm just going to leave this for now. I don't know if I'm going to come back to it or not. If you want to read about it, it's fine. It's in the notebook. It tells you how to do some other things that might be useful when you're using these functions. But I really want to move on to the dynamic memory allocation so that you can actually complete the assignment. Right? So the next notebook after this one is the dynamic memory allocation notebook. All right, so you know that in C, that if you just create a little local variable in a function somewhere, it has automatic storage duration, right? So in other words, you make the variable in a function, it lives for the length of the function and then goes away. So if you need a function that computes an array of some kind, or for example, or computes a string of some kind and would like to return that array or string, you can't just make a little local array to hold that string or array, right? You have to do something else. So the something else that you need to do falls under the term dynamic memory allocation, right? And so when you are using dynamic memory allocation, you're creating an object having what's called allocated storage duration. So allocated storage duration is the lifetime of an object that is under control of the programmer. The programmer controls when it's made. They control when it goes away, right? By goes away, I mean, when do you get rid of the memory associated with that object, right? So to use dynamic memory allocation, right, the programmer is now responsible for everything, right? So you are responsible for, number one, asking for the memory for that object, right? So you need to ask for enough memory to hold the object that you want to create. This is C, so you have to do everything on your own, right? You now have to, you've got some memory for your object. You now have to create the object and fill in whatever, and then give it whatever value or values you require, right? So if you make an array, you now have to fill in the contents of the array, right? If you make a structure, you have to fill in the contents of the structure, so on and so on and so forth, right? Now you've got your object, so you can use it in your program, right? So now you can pass your object around to whatever functions are needed, right? And then when you're done with it, assuming you actually know when you're done with it, right? You have to remember to release whatever resources were used to create the object, right? So if you allocated memory for the object, you now have to give the memory back to the operating system, right? And so all of the responsibility falls on you now as the programmer, right? Languages like Python and Java, they take care of this last step for you, right? And so they both of those languages were created with the desire to take care of this problem for the programmer, because one of the most common bugs that you get in a language like C and C++ is that you forget to deallocate the memory for some object that you created during the lifetime of the program, right? If you forget to do this over and over and over and over again, right, you end up running out of memory, right? Or your program consumes a lot more memory than it requires, right? Yeah, so languages like Java and Python, they try to get rid of unused objects for the programmer automatically. Right? Now, to do this sort of thing, fortunately, there's not much you need to know, right? You need to know how to allocate memory. You need to know how to free it. So to allocate memory, there's only three functions that we need to know about, right? There's something called malloc, there's something called calloc, and there's something called realloc, right? The first two work in a similar way, right? They do something slightly different, but they work in a similar way. The third one works, it's similar to the first two, but it does something special. So let's take a look at what they do. There's, in newer versions of C, you've got other versions of these functions as well. Okay, so malloc is I guess it's this, I don't know, is it the most common? It's the standard one it's the standard function that you're going to use when you need to allocate a new object, right? Brand new object, right? So if you want to allocate a chunk of memory for an object, right, you can use malloc, right? So malloc returns a pointer to the allocated memory, assuming it succeeds, right? So if malloc can actually get you a block of memory that's big enough, right, it returns a pointer to the start of that block of memory, right? How much memory do you want to allocate? Well, it's that value size, right? Remember, size is always measured in the multiples of a car, right? So if you want an int, you're going to malloc enough memory for the size of int, right? If you want two doubles, you're going to allocate enough memory for the size of two doubles. Right? Okay. you should not pass in 0 for size, or if you do so, you have to remember you can't do anything with the returned pointer, right? So in C, there is no such thing as the 0 length, or there's not supposed to be any such thing as the 0 length array, right? Or there's not supposed to be anything such as the 0 length block of memory, right? So when you call malloc, you're not supposed to pass in 0. It works on most implementations, right? The standard says the value of the return pointer is implementation defined if you pass in 0, right? So it works, but you can't do anything with the pointer, right? So you should generally avoid passing in 0. So you get this pointer back, right? It has type void star, which means points at anything, right? You can store this pointer in whatever pointer type you want, and you don't need a cast. Right. So if you want an int, you would allocate enough memory for an int and store the result in a pointer to int. Right. So let's look at an example here. Here I've got a structure, right? Point 2. And I'm going to allocate enough memory for that later on down at the bottom here. So here's a function. This is in the main function so that we can run it in the notebook. But you can imagine this is in some other function, right? So it's not necessarily in main. There's our call to malloc, right? So malloc1 allocates enough memory for one single character, right? So it's not a proper string for sure. Well, sorry, it could be the empty string, right? What does it return? It returns a pointer to the memory, right? To the start of the memory. I can store that pointer in whatever I want, right? In whatever pointer type I want. So if I want to allocate memory for a car, I should store that value in a pointer to car, right? And so C points at the memory that was just allocated for my one character, right? Let's read the comment here if I can get to the scroll bar. Where's my scroll bar? Oh, there it is. Oop. Okay. So this thing here has allocated storage duration. So the lifetime of this car object, right? The lifetime of the memory that was allocated by malloc, right? Is the lifetime of this program, right? Sorry, it is the goes until the programmer manually frees the memory allocated to that object. Right. Okay, so I've got a pointer to a car. So what can I do with it? So in this case, I really do have a car object, right? That car object is sitting in whatever memory was allocated by malloc, right? So that means I can write into that memory. I can read into that memory if I want to, right? Now you have to remember that you've got a pointer to that memory. So you're going to have to dereference the pointer in order to write into it, right? So dereference C, right? That gives me the memory allocated for the character C, or for the character, and now I can put a character in that memory, right? So I can write the character A into that block of memory, right? If I dereference the pointer, I can get the value of the character that's sitting there, and I can print it in this case, right? So if I run this, I'm going to get that C points at character called A. Okay. The free function frees the memory that was allocated for the object, right? So in other words, when you call free, you're going to kill the object, right? So freeing that character that I allocated back here, right, means that the memory that was reserved for that character is no longer reserved for that character, right? It's returned back to the operating system. You can no longer use our pointer C safely here, right? So once you free the memory that's pointed at by C, right, you can't do anything with C afterwards, right? You can reassign it to another to something else, and that's fine, right? But you can't dereference C at this point, right? Whatever C was pointing at is dead, right? The lifetime of the object ends immediately after free returns, right? So don't use C here, right? Unless you reassign it first. Okay, what if you want to allocate one int? All right, so you allocate enough memory for one int, right? So you have to say size of int here. As soon as you allocate that memory, you've got an int, right? You don't know what is in the, you don't know what value the int has, but you've got one, right? So that pointer I really does point at an int now, right? Or I guess more precisely, it points at memory that could hold an int, right? It's up to you to fill in that memory, right? So now I'm going to stick the value 99 in that int. Right? If I dereference I should get 99, and I do. Right? I'm going to free I here, which means that whatever memory I was pointing at is no longer is no longer valid. Right? So in other words, I can't use I or dereference I to get to that memory anymore. Right? There's a double. It's the exact same thing. Right? You want to allocate a double, you allocate enough memory for the size of double. Right? Here's a structure. Right? If you want to allocate a structure, it's just size of and then the name of the structure. Right? So here it's size of struct point2. Right? When you have a structure, when you have a pointer to structure, right? Remember that you can get to the members of the structure using the arrow notation. Right? So hyphen greater than dereferences s for me, right? And gives me the member variable x, right? So I can write in 0.5 to that value, to that member, right? S hyphen arrow, greater than y, dereferences s for me, gives me the member y, right? And I can write in minus 9.9 there, right? And so when you print out the point here, you get out the point, 0.5 and minus 9.9. Right? So there's how you use malloc. If you want an array, right, you can use malloc as well, right? You just allocate enough memory for the elements of the array. Right? So here I would like an array of size 8, right? And this is going to be a string, right? So I want a string that can hold 7 characters. Right? Okay. Malloc n, right? Remember n is, so if I just use n, that's just 8 in this case, right? That's 8 cars in this case, right? So now I can copy the string CISC220 into C just fine. Right? If I print the string down, oh, sorry, I haven't run this one yet. If I print the string, that works just fine. Okay, suppose you want an array of int, right? So here I want an array of 3 ints, it looks like. Right? So if I want an array of 3 ints, malloc 3 times size of int. Right? And now you've got enough memory to hold 3 ints. Right? You can treat that I as though it were the name of an array. Right? So I can write the values 1, 10, and 100 into that array. Right? And then I can print them out using a little loop here. Right? And when you do that, right, you see that I does in fact hold the values 1, 10, and 100. Right? You do the same thing for double. Right? There's an array of 3 doubles allocated dynamically. Right? Once malloc returns, you can fill in the values. Right? And then you can print them out afterwards. Right? You get that. And you can do the exact same with a structure. Right? So allocate enough memory for 3 points. Right? And now go ahead and fill in the values for those 3 points. Right? Print them out, and there are your 3 points. Right? So if you need to return a string or an array from a function, you're probably going to use malloc or calloc to allocate the array. And then you can return a pointer to the first element of the array. Right? So any function that wants to create a new array must return it dynamically. Right? So here's my function int array. Right? It allocates an array of size length, right, and returns a pointer to the newly allocated array. Right? Remember, there are no 0 length arrays in C, so we probably shouldn't try to call malloc with 0, or we should try to avoid doing it anyway. Right? So this is always going to return an array of at least length 1. Right? Call malloc. Right? Here, I'm just going to write in a value into the first element so that when I print out the contents of the array, you actually see something. Right? And now you can return that pointer back to the caller. Right? So that's how you make an array and return it back to the caller. Right? If you wanted to return an array of double, you would just malloc an array of double instead. Oh, wait, what's going on here? Int, there's a bug. Size of length times size of int. There we go. That's better. Okay. Run that, and there's your first element in the array. And so here the caller has asked for an array of int of length 10. Right? There really are 10 elements there. Right? So if you were to print them out, I'm going to print out the last one. Right? So malloc, so in this case, so this is deceiving. So if you run a little test program like this, right? If you're in Linux, you're almost certainly going to get zeros in the array, right? So here I printed out the last element of the array and it happened to be 0, right? Malloc does not initialize the memory that's returned, right? So if you allocate a chunk of memory, you still have to fill in the values before you use the values, right? Or you have to assume that the values are unset when you use the values, right? So malloc does not initialize memory for you. So that's one way to return an array from a function, right? There's another way to do it, right? So the other way to do this is to ask the caller, right? So the caller wants an array, so you can ask the caller, give me a pointer in which I can write into to tell you where the array actually is or where the array starts, right? So one more time, give me a pointer so that the function can write into that pointer to tell you what is the address of the newly allocated array, right? So if the caller needs the function to write into a pointer, the caller must provide a pointer to a pointer, right? So here, we're going to allocate our array, same as always. Oh, we're going to screw it up again because I forgot the size of. Times, sorry, length times size of int, right? So we're going to allocate the array the same as always, right? I'm going to write a value into the first element of the array, right? But now, instead of returning the pointer buff, right, I'm going to write the pointer into a pointer provided by the caller, right? So if I'm going to write into a pointer that's owned by the caller needs to give me the address of that pointer. In other words, they need to give me a pointer to a pointer, right? Which is what this double star is doing here, right? So int star star is a pointer to a pointer. Right? Remember, pointer is just a memory address. So if I want to write a memory address into something, right, owned by the caller, they need to give me a pointer to that memory address, which is a pointer to a pointer, right? So here's the caller's pointer, right? I want to write in the address of the array that's been allocated into A. So they need to tell me what is the address of A so that I can actually write into the pointer. Okay. Run that, and everything works the way you expect it to. Right. So that's the other way to return an array from a function. Right. Have the caller pass in a pointer to a pointer so that the function can write into that pointer to indicate to tell the caller where is the start of the newly allocated array. You might wonder why you have to you might wonder why you would write this if you could always write this instead, right? Because the first one is a little easier to understand, right? Okay, I got a function that's just going to return a pointer, right? And the answer is that like always, it's often useful to return more than one piece of information at a time, right? So if you needed to allocate an array and you needed to tell the caller how big the array was, right? You now have to return two pieces of information. So one of the two pieces of information has to be returned by pointer, right? Whether it's the array or the size, it doesn't really matter, right? You're still working with pointers in the end. Okay, notice here, the pointer to a pointer syntax may be confusing, right? And so so this goes and expands on this again if you want, if you're still confused about how this is working. Okay. Okay. If you go and read the documentation for malloc or calloc or realloc, they all tell you if this function fails to allocate enough memory, null is returned. Right. So in most introductory textbooks, and even a lot of the advice you'll see online, right, you will be told every time you call malloc or calloc or realloc, you have to check if the returned pointer is null, right? So in this case, I'm going to allocate a string of length 1000, right? I guess like 999. And I'm going to check, okay, so did malloc succeed, right? So if not str is true, then it failed, right? Malloc was not able to allocate enough memory for this string, right? And so people will tell you, look, this is what you should write. What they never tell you is, what do you put in here, right? Okay, so malloc failed, so now what, right? And so the advice for what to do for the now what is basically it depends, right? And so it really depends on the program that you're writing, right? The real issue here is that, look, if malloc failed, right, and you're allocating something that's not terribly large, then you've got bigger problems than malloc failing, right? Essentially what's happened here is that your system has run out of memory. And there's nothing you can really do in this case anyway, right? So in a typical user land program, like PowerPoint or something else, your text editor, right? If it needs to allocate some memory and it can't, there's nothing the program can do to fix the problem, right? The only sensible thing to do is to stop, right, somehow. If you're in a program like PowerPoint or something, it would be nice if it saved your file before it crashed, right, or exited. But you don't really have any recourse, right? So there's not much you can do in this case anyway, right? So the basic line of thought is that the allocation function has failed because the operating system cannot satisfy the memory request, right? If your operating system's out of memory, you've got bigger problems than malloc failing, right? There's nothing you can do. So in this case, it doesn't really make sense to check for null, right? There's probably nothing you can do anyway, right? If you want to try to do something about it, right, then what you should try to do is you should try to shut your program down cleanly, right? You can't recover from the fact that you're out of memory. You should probably shut down the program, right? And so the function exit will do that for you, right? So exit, pass in a value, will set the exit status for your program, right? It'll shut down the program, it'll release whatever resources are used by the program, and then it will exit to the operating system. It returns this value back as the exit status of your program. So in Linux, this is the exit status of the process. Exit failure is just some standard value. I don't know what its actual value is. It'll change from compiler to compiler. Right. So if you really want to check for failure of memory allocation, right, and then you want to shut your program down cleanly, just use exit to do so. Right. Now, there's a blue box here. Almost universally, you will be told you should always check if your pointer is null after calling malloc, right? Now, the problem is the only operating system where malloc actually returns null is Windows, right? Linux won't return null from malloc. Unix won't return null from malloc. Mac OS will not return null from malloc, right? In all other operating systems, here it is. In all other commonly used operating systems, the standard memory allocation functions, so malloc, calloc, and realloc, they never return null. So there's no point in checking for it anyway. Because what happens is when those operating systems start to run out of memory, the operating system starts to kill off processes that are using memory, right? And so malloc never returns null, right? Which means this test is never true. So there is that to consider as well. There's a link here. There's a research paper that actually shows that this is true, right? If you're interested in reading about that sort of thing, just follow that link to check out and see how to see the details of what they actually did, right? So this advice of checking for null is what's the best term for this? I guess it's outdated. It's probably not necessary anymore, right? Unless your operating system suddenly change, right? But most operating systems never return null anyway from the memory allocation functions. Okay, CAlloc is basically like alloc, except it happens to zero out all of the bits in the allocated memory. So if you want your memory to be allocated to some nice default value, namely 0, use CAlloc instead. The way you call CAlloc is something slightly different, right? So it's CAlloc, right? It is the number of elements that you would like to allocate, right? So if you want 1 car, you pass in 1 here, right? You want 1 int, you pass in 1. If you want an array of length 10, you pass in 10. And then you tell it how big is each element, right? Num is the number of objects, size is the number of bytes of memory request. Yeah, right. And then size is the size of each element, right? Pretty sure. Yes, right. Again, num times size should not be equal to 0, right? So the total amount of memory allocated is num times size. Right. So to use CAlloc, if you want to allocate 1 car, I want 1 car, right? So 1 car, each car takes up 1 unit of memory. Okay. Here I want 1 int, so 1 times size of int, 1 comma size of int, right? Here I want 1 double, so 1 size of double, right? And in the 4th example, I want 1 structure, so 1 size of structure, like 2. And away you go. Otherwise, the example is exactly the same as the previous one. Right? If you want an array of int, I probably screw. Oh no, look, I got this one right. Okay, if you want an array of int, right, of that many unsigned ints, sorry, right, I want that many unsigned ints, right, and that will work. And so you, and CAlloc will always zero out the bits of memory, right? So if you have ints, all the ints will be 0. If you have doubles, all the doubles will be 0. If you have Boolean values, I guess they're all false, right? Because 0 is false for Booleans.